Okay, another case of permutations, a special case, instead of arranging objects in a line, we'll arrange them in a circle. And this changes the number of ways we can arrange it. So what is the difference? Okay. Basically, it's how you place that first object. Because when we have a line, okay, so say I'm going to arrange 6 objects, how many ways can I place that first object? Well, there's 6. And that's because there's a start and a finish of a line. So I can define each spot. I can say, well, that's the first spot, that's the second spot, and so on down to the 6th spot. So there's 6 ways I could do it in a line. Whereas when I'm talking about a circle has no beginning or end. So I can't define the positions until the first object is placed. So there's only one way of placing the first object, and that is in the circle. Then once that object's placed, I can now define the other positions, because I can say, oh, well, 1 to the right, 2 to the right, and so on. So it only has one way. So how does that change things? Well, in a line, we know the objects went n for the first one, but in a circle, it's now going to go 1. The second object, n minus 1, it's now going to be the same. And so on until we get to the end. And so basically the difference is we can see in a line we've got n factorial, but in a circle we have n minus 1 factorial. So it's n factorial divided by n. I guess that's because that's the number of ways we could have placed the first object if we were placing it in a line. So it becomes n minus 1 factorial. So that's all we really have to do. If it's in a circle, it's 1 less factorial number of objects. So okay, we're in a meeting room. We've got a round table surrounded by 10 chairs. Committee of 10 includes 3 teenagers. How many arrangements are there in which all 3 sit together? Okay. So look after the condition first. The condition is these 3 teenagers want to be by themselves. Well, together. So there's 3 factorial ways we can arrange them together. Now we haven't placed any objects yet. All we've done is we've decided how the 3 teenagers are going to be together. So 3 factorial. But now it'll be times 7 factorial because I'm now going to put the objects in the circle, but I no longer have 10 objects. I now have 8. The 3 teenagers are like one group now, plus the other 7 objects, 8 objects. But it's in a circle, not a line, so it's 7 factorial. So there we are, 30,240. We're going to hold elections for chairperson and secretary. What's the probability that they are seated directly opposite each other in this circle? Okay, well, no restrictions would be 9 factorial. Right? 10 people in a circle, so it's 1 less, 9 factorial. Now, work out the restrictions. Let's say the president. Well, they can sit anywhere. They're the first person we're going to put in this circle, so there's just one way of doing it. We're going to put them in the circle. But now we're saying the secretary's got to be opposite. So there's only one spot now that the secretary can go, straight across from wherever the president decided to sit down. That leaves us with 8 people to sit. But it's no longer a circle because we've already placed objects in. So we've defined the spots. So it's like a line now, 8 factorial. 8 objects going into these spots. So 1 times 1 times 8 factorial over 9 factorial, which gives us 1 in 9. Of course, there is a simpler way. Probability that the secretary is straight across from the chairperson, well, the president or the chairperson, see how we keep changing names, president, chairperson, well, whichever it is. The president sits down, what's the probability that the secretary sits across? Well, there's 9 chairs, so there's a 1 in 9 chance that they sit across. Sometimes logic can solve these problems a lot quicker. Here's an HSC one. 7 people this time going around the table. How many are possible? So no restrictions. Well, it's a circle, so it's 1 less, 6 factorial. 720. 2 people, Kevin and Jill, refuse to sit next to each other. Don't like him, don't like her. How many seating arrangements are possible? So we've got to look after the condition. But what is often easier, rather than working out how many ways that they're not together, Work out how many ways that they are together and subtract them from the total number. So I'm going to work out that. So if they are going to be together, we're now saying they are together. So put them in their little group of two factorial ways of doing that. They now become like one object. And so we've got our little group plus 5 other people, so 6 objects all up. But we're putting it in a circle, so it's 5 factorial. So 2 factorial, 5 factorial, 240. But remember, that's not what we actually wanted. What we actually wanted was the number of ways that they're not together. Well, we worked out there was 720 all up. So therefore, number of ways not together, 720 minus 240, 480. Here's a little bit of a flow chart, how to approach these different problems. Permutations and combinations, right? So items are chosen without replacement. That's the first thing you have to realise. As soon as you start putting things back, it's no longer a permutation or a combination. You have to use the basic counting idea. Because all permutations and combinations is without replacement. Now, if they're without restrictions, then we know permutations is when the order is important, combination is when it's not important. Then over here, we go talk about permutations. Is it in a line or is it in a circle? If it's in a circle, well, it'll be one less. And then some of the things we've looked at when they're in a line. Do we use all of the items or do we just use some of them? And when we just use some of them, that's where we introduce the idea of NP. Well, they've used R here, we used K. All of them are used. Are they all the same? Or are there some different ones? So n factorial if they were all different. But if some were the same, we then divide it by the number of ways. So I guess that's all the different types that we've looked at so far. This was from the 1995, as you can see. I thought it was a nice little question. We've got 8 buttons labelled A to H, and you're given a 3-letter code. How many codes are possible if you can repeat the letters, and the order is important because you're going to be pressing the buttons. You're going to go bang, bang, bang to open up the whatever it is this lock is locking. Well, in this case, it's with repetition. Like I can reuse a letter. There's nothing stopping me going D, D, D. So it comes down to the basic counting idea. So it'll just be 8 times 8 times 8, 512. How many different are possible if they can't be repeated? So maybe the order is important, but the button stays down when you press it or something like that. So you've got to have different letters. So now it becomes a permutation. So 8p3, could have still used the basic counting idea. Could have gone 8 times 7 times 6, because that would give me the same value as 8p3. 336. Now it's saying this lock operates, you've got to hold 3 buttons down at a time. So obviously you need different letters, but the order no longer is important now because we're pressing all 3 down at once. So it now becomes a combination. So 8C3, only 56 possibilities now. So I think that particular year, some people who really had no idea, or they might have had a little bit of idea, just wrote down the same answer for all 3, and they figured, well, I've got to get one of them right. You know. Okay, so 10I. So